Let's look again at what it means to find the area between the two curves. So the area between the two curves is this yellow shaded area. And I'm going to go back to basics again. So I'm going to say, all right, to calculate the area of this, I am going to make a whole bunch of rectangles, and I'm going to add them all up. And the area of a single rectangle, so the area of a single rectangle is length times width. Length times width. And the width of this rectangle we're going to make small, and we're going to call dx, a little sliver dx. So the width is dx, and the length is this distance right here, which is the y, call this the upper bound, and this is y of the lower bound, or so the length is y of the upper bound minus y of the lower bound. And we're going to say, all right, that was the area of a single rectangle. Now we're going to add them all up. I'm just going to actually erase here. We're going to add them all up, which I'm going to use the summation symbol. And then I'm going to make this really small. So make these rectangles slivers and take the limit as the dx goes to 0. And what we're doing there is we're integrating. It's adding the sum of really small rectangles where y of the upper bound minus y of the lower bound dx, and we're going between this value and this value. So that's the link between areas of rectangles and integration. Now the y values we have equations for. The upper one was the f function, and the lower one was the g function. And we're going from a to b. So now I want to turn this problem on its head, and we're going to do it one more time, but this time I want to think of it in terms of adding. So that's this is f of x, make this green one here, g of x. Instead of adding rectangles that are vertical, I'm going to make them horizontal. So I could do the same thing by estimating a whole bunch of rectangles that are lying on their side. Right? So in this case, we're going to do the exact same thing. The area of a single rectangle is length times width. This time the width is defined by this value right here, this little distance here, which we're going to call dy, because it's a little sliver on the y-axis. So the width is dy, and the length is the difference between this point and this point. In other words, this length here. So that's the right hand x value subtracting the left hand x value. So xr minus xl. And I'm going to add them all up and make this really small, and that means I'm going to integrate. So it's xr minus xl dy, but instead of going from here to here, we've got to go think of it in y terms. So we're going to go from this point to this point, because we're integrating over the y-axis. So from c to d. Now, why do you think, Sylvia, why did I do this? why did I do this when I had a perfectly fine method of already calculating the integrals? And I think that in the example that's going to follow, you'll see why this method would be easier than the method we did in the first few videos.